Yes. Mr. Fuller, welcome.
Thank you, Dimitros, and hello, everyone. Welcome to the session today. I want to take 45 minutes just to elaborate on some concepts and components that Ronnie spoke about in her keynotes this week, and take a quick look at some of the attack tools and techniques that we come across on a day-to-day basis. So with all that said, I shall share a presentation just to give us some extra context of what we'll be looking at today. And then we'll get into more detail as we go through the session. So I'm going to share my screen. So as we mentioned, we're going to be talking about solutions that deliver less fraud, less friction with less effort today. And to start, I want to talk a little bit about the malleability of online digital identities today. We're very familiar now with how easy it has become to manipulate many different facets of our online identity, including things like taking a slightly terrifying version of Jennifer Lawrence and mapping Steve Buscemi's face on. There are tools that are available to manipulate our identities online in a very easy way. In fact, while I was struggling with lockdown here in the UK, I couldn't make it to a hairdresser's. I can grab some of these tools and make me a little bit more presentable on the Zoom calls that I've been attending. Now, some of the components that we are familiar with as we interact that try and ascertain and prove our identity online can introduce a lot of friction. And a great example of that is capture. We're all familiar with capture, always seems to happen at the worst time. We have to click the squares and the grids. So the challenge with capture is not just that it's quite frustrating as an end user, it's actually pretty easy to bypass as an attacker. So if you're familiar with services like TwoCapture or Death by Capture, they allow you effectively to solve captures at scale, often around 1,000 captures for less than $1. So capture is not only slowing down your users who are desperately trying to access your services, it's also not really that much of a challenge for attackers to bypass. And we'll take a look at some of those techniques in a second using TwoCapture. The next step in the evolution of this corruption of our digital identity are tools like the Genesis Marketplace and the Genesis Malware. So Genesis as a component doesn't just steal our usernames and passwords. The malware is designed to steal a lot of other details from our identity. So if you're unfortunate enough to download the Genesis malware, it's going to intercept the usernames and passwords that you use on websites, but it's also going to intercept a lot of the components about or details and data points about your environment. So things like the browser version that you're using, your screen resolution, the size of the browser window within that, your CPU, your RAM, all of your cookies, and all those other data points. The reason that the Genesis malware does this is because they know that these data points are often used to prove you are who you say you are. So by stealing and intercepting these data points and selling them through the marketplace alongside the username and password, it makes it much, much easier for attackers and fraudsters to look exactly like us online. So to come back to some components that Ronnie mentioned earlier in the week, Shape and our work with F5 is designed to force attackers to answer 3 questions. The first of those is, are you human? And this is something that we've been doing as Shape for the last decade. It's very accurately determining effectively the difference between a genuine human web or mobile interaction versus a fraudster or an attacker who's trying to look like that human at scale. So effectively bots and automation. Once we've done that, we can look at whether the human behind that request, once we've removed the automation, is good or bad. And we'll talk a little bit about some of the signals that could be used to do that in a second. But fundamentally, once we look at the human transactions in isolation, how do we determine whether this is a good human who's genuinely trying to access your web or mobile service versus a bad human just trying to defraud someone? And then finally, a bit more about that identity component. Once we've answered those 2 questions, we can look at, are you who you say you are? And this is really useful as we look later in the session today at friction, because if Chris is logging back on and we can accurately ascertain that it's Chris on the same device and it's safe, why do I need to re-authenticate quite as frequently as I do? We can make that process a lot easier, and that's much more likely to encourage me to use those web and mobile services. So by forcing attackers and fraudsters to effectively lie their way through these questions, we can remove bots, we can remove forms of human-driven fraud, and then we can reduce the friction for legitimate users all the way across your web and mobile application journey. So we'll be looking a little bit more at those components today. To look at the are you human component first. Now, it's tricky for a WAF to stop this problem because effectively it's very hard to tell the difference between me logging in with my own user and password versus a bot who's or an attacker who's using bots and stolen credentials to do the same process at scale. From a WAF and even your application origin perspective, all that's happening is somebody is entering in the username and password and clicking submit. A WAF and often your application logic is not designed to determine the difference between those two types of request. So that's where Shape comes in order to determine very accurately the difference between those without creating false positives and false negatives. The reason that these are challenging for WAFs to identify is graphs like this, where we see effectively good human traffic in the green at the very bottom of the graph. And if you take a look at your own data, this is what you should expect to see. You should expect to see that diurnal pattern of humans coming in and logging in during the day and logging off at night. So it's always worth looking at your own traffic to make sure that you understand the patterns of regular users. The challenge here is that what our customer actually saw is this attack traffic in yellow. It's random, it increases at certain points without any known reason. They couldn't correlate this data to marketing campaigns. So what the what the Shape customer was actually seeing was a volume of automated traffic, very different to that human legitimate diurnal pattern of green traffic that was logging in and compromising accounts. In fact, this particular graph that represents the login page of this particular customer, there were over 64 million unique login attempts, and the attack traffic is coming from over 500,000 unique IPs, from almost 10,000 9.7 source networks, pretending to be 95,000 different unique user agents. So if you're trying to block this manually or do geo-blocking or IP reputation or rate limiting, attackers are very cognizant of those techniques. And that's why they use such vast networks in order to commit their attacks. So be aware that the attackers know exactly how to bypass those existing controls and commit these sorts of bot login attacks at scale. When we at Shape look at how we mitigate these sorts of attacks, we fundamentally draw data from three key areas. Firstly is the environment itself, the device. How do we understand, is this truly version 89 of Chrome? Or is this an attacker who's trying to spoof some of those components in order to commit a bot attack? As you've seen, attackers create very vast attacks using hundreds of thousands of IP addresses and source networks in order to log in many millions of times. The reason that attackers need to do that is because they are often going through hundreds of thousands or millions of credentials to see which ones work. Not every user has a username or password that is shared across all their different services. So attackers need to crunch through many of those credentials in order to figure out which ones of those they can resell. So that's why we see such scale. To achieve that scale, attackers need to create spoofing. So that's why we're drawing these environmental data points in order to spot the spoofing and forms of emerging patterns that can help us identify those attacks. In the second column, we look at the behavior. So the actual user interaction pattern on web or mobile. We'll look at this in a second, but this is mouse movements, key cadence, key presses, and then finally the network layer as well. Although HTTP headers are finite in their length, we can look at some of those data points just to make sure that they're accurate and consistent with the environment. So these are things like if I create an emoji on my device, there's actually a wide range of different rendering things that can happen depending on your operating system and your browser. So we can look for the signs of those spoofed emojis. If the user agent is reporting itself as version 89 of Chrome on Windows, and yet we're seeing the emoji render in a funny way, this is where we can start to spot those spoofing that attackers have to go through in order to identify those attacks. Doesn't mean that we're going to flash a big emoji in front of your users, but it does mean that we're going to render those in the background to make sure we understand the difference. Same for floating point mathematical operations. Different browser engines, different JavaScript engines and browsers will compute that to different degrees of accuracy. So if you understand those components, you can see again these signs of spoofing that emerge. So Shape has invested many hours and hundreds of thousands of hours into understanding these environments in great detail and collecting these data points in order to understand these attacks. These are just a couple of examples, but really this comprises of hundreds of different data points that we can use to understand these signs of spoofing. The same goes for interaction patterns. So you'll see in the top two boxes what looks to be a more human-like interaction. There's key up and key down events represented in blue and orange. Those have a natural cadence. They don't all happen together. There's different gaps as the user is typing. When the mouse moves in that middle box, you'll see that happens in a nice arc. It doesn't happen at the same time as those keys are being pressed. If we compare that to a bot at the bottom, what we'll see is that, number one, the mouse and the keys are being pressed at the same time. So either this is a three-armed user or it's a bot. Equally, the keystrokes happen in very quick succession. They're very regimented in their pattern, and the mouse is moving in a very straight line without actually movement in between it. So it's fairly easy to spot in this sort of context the difference between a legitimate user interaction and a bot. However, what we're seeing at Shape is the way that now attackers are contriving entropy into their interactions. So a good example of this is an attack that we saw recently, where an attacker, whenever they click the login button to try and check their stolen credentials, they would make sure that the coordinates of the click location on the submit button moved down by 3 pixels and across by 1, again, to avoid creating the sorts of patterns that we would expect in the text. So even when that sort of scenario emerges, as we expect the randomness and the contrived entropy of attackers, that's where Shape's machine learning is designed to come in and detect those new emerging patterns and mitigate those forms of attack. So I'm going to take a pause there. We've talked about a couple of components today in terms of interaction patterns and attacks and capture solving. So I want to explore some of those in a bit more detail. So I'll stop that share. Let's just take a look at my screen as I share my desktop. So what you will hopefully see in front of you is an example of one of these tools. This is called Browser Automation Studio. You can go ahead and download this off the web. Of course, I'd very much recommend that you do that in a virtual machine that's not connected to anything sensitive. What's interesting about Browser Automation Studio is that it's effectively a graphical user interface that allows us to do different browser interaction patterns, as the name suggests, browser automation. It makes it very easy. So what I have in the left grid here is some logic that I've put together in the past that effectively is going to ingest a resource, which is a list of usernames and passwords in a CSV file. It's going to do some list manipulation to set that list position and iterate through every line of credentials in that list. And then it's going to load a test website of mine and enter in those credentials. Now, I want to show you what's unique about that pattern as we have it. So you can see that the logic is fairly simple. If you've got a rudimentary knowledge of list handling and interactions and browsers, you can work your way through this very easily. It's very easy to type text. All of these different components are actually in this top grid here. So this is where I can do things like define my interaction patterns. I can load a page. I can reset. I can manipulate the page in different ways. I can insert JavaScript. So all the different ways of interacting with pages and files and adding header fingerprints are built into there. And what you'll see now in this bottom grid, as I start to commit this attack, is that Browser Automation Studio is going to start iterating through these logic block steps and loading my demo site at the bottom. So I want to move my mouse out of the way, and it is, because what I want you to see, hopefully it might be a little bit small, but you can hopefully see the way that the cursor is moving through that page. So with very little effort as an attacker, I am creating an interaction pattern that looks fairly unique. It has a typing cadence that you can just about see. The text doesn't all appear at once. There's a cadence to it. It's randomized. The mouse will move. down to the submit button and click submit. It takes a bit of time. This is a bit of effort that not every attacker is going to go through, but for those motivated attackers who really want to bypass your controls, you can see hopefully how easy it is for an attacker to start creating what looks like fairly human-looking interactions. So just to come back to the point, don't forget that attackers are fairly capable of looking and creating these very unique-looking attacks, and they will do so fairly easily. And as I say, you can go and grab a copy of Browser Automation Studio, or take a look at the many videos on YouTube in order to see exactly how this works. So one last point of Browser Automation Studio before I just move on to some points about capture is at the bottom you'll see that we've built in some logic to intercept the response from the page and take a look at whether the login worked, and therefore we can understand whether this attack pattern has worked or not. So we're intercepting response in this particular instance. We have effectively intercepted that response and understood and logged out to the log at the bottom whether this attack worked or not. So as an attacker, I can run this in parallel. I can proxy the request through many different proxies, and I can come back later and see which of those credentials are working for me. So I'm going to stop sharing here, and then we'll talk very briefly about capture. So I want to share my screen once again. What I want to also take a look at is the capture solving component we spoke about a minute ago. So as I mentioned, it's fairly trivial for attackers to bypass capture solving techniques. So or to outsource those capture solving techniques. So one of the examples that I mentioned was TwoCapture. So TwoCapture is a service that you can go online and sign up for. And what TwoCapture effectively does is grabs the capture request, sends it off to a real human who's going to solve that for you, and then gives the response back. So it's very easy. It takes a bit of time, as you can imagine, because it's predicated on a real human solving that capture and giving the response. But as an attacker, if I create enough parallelism, I can solve these captures fairly quickly using this technique. So what you see in front of you here is a little bit of node scripting. I'll put my hands up immediately and say that I'm fairly awful at scripting, so please don't use any of this as an example. But the point is here, in about 40 lines of code, including a few comments, we have created a script that can bypass the capture. So all that's happening here is that we're going to create a new Puppeteer instance. Puppeteer is a way of driving a headless browser. So we're going to be driving a version of Chrome. I'm going to be using a plugin, actually, that I downloaded from GitHub called Recapture from the Recapture Extra or Puppeteer Extra group. So take a look at Puppeteer Extra on GitHub. It's lots of different tools that you can add into your Puppeteer script, including what effectively is this nice node component and code block that's going to solve this capture for me very easily. So this is abstracting all of the logic that I'd have to do in order to solve a capture manually, and this is going to create the API calls out to TwoCapture for me nice and simply. Otherwise, we're going to set some variables. We're going to instantiate a version of Chrome. In this particular case, I want to see what's going on. So we're going to be using a non-headless browser, if that makes sense. If I wanted to use proxies, I can add that logic in there. And otherwise, we're going to be doing a very similar thing as we were doing with Browser Automation Studio. We're going to be loading up a page, interacting with the form elements on there, and then we're just going to be using this very easy solve block in order to create the API request out to the TwoCapture service and grab the response and solve that capture. So let's take a look at that running. So we'll see this fire up in just a second. So a new version of Chrome is being fired up. Here's our interaction. Now you'll notice here that that interaction looked a little bit more robotic. It happened very quickly, it's very regimented, there was no mouse movement. So we haven't done quite as good a job here as creating a human-looking interaction. But we can do that with a bit of manipulation of the key events in Puppeteer if we wanted to do that in the future. What's very important here is you'll notice that the reCAPTCHA icon has turned purple. We've been a little bit lucky today. That solve happened quite quickly. But what effectively happened is the reCAPTCHA plugin has colorized that icon. So we know that the solve is in process. What the reCAPTCHA plugin has done is grabbed the unique token from that particular capture call, sent it off to a human who solved that for me. So relying really on low wage environments in order to commit these attacks. But that human has solved that capture for me. They've sent the token back, and the TwoCapture reCAPTCHA plugin has intercepted that, filled in the capture for me, and then submitted the credentials. So again, just to come back to the point, relatively easy using a couple of components, in this case, TwoCapture as a service and the reCAPTCHA plugin for Puppeteer to solve those captures very easily for someone like me, who again has very limited talent in scripting. So final point before we move on to talking about fraud, as I load up one final screen, is to look at some of the data points that we collect in order to ascertain whether something is from a bot or not. One point I'll make about Shape is that we found the most effective way, for the most part, to solve this problem for our customers is through a service. So we will continually monitor the attacks that happen to our customers. We use machine learning and layers of human oversight in order to detect new forms of attack. And then depending on the way our customer wants to solve that problem, we'll either go ahead and react automatically and mitigate that attack in real time, or we can check with them or provide levels of service that solve that over time. So I want to show you very quickly, fundamentally, what some of that data looks like, but understand again that in the back end, through our data processing and data pipelines, is where we're using machine learning to understand and identify and intercept new forms of attack and automatically mitigate those for our customers. So final screen share, and then we'll be heading back to the browser, or the presentation, I should say. So this is just some of that data from one of our that demo site that I showed you through Browser Automation Studio. I was a bit cheeky. I wanted to show those logins either working or failing, so I've used a bypass switch that I've built into the configuration of this particular demo site, which means that we won't see us mitigating. But this is the portal that some of my customers come in to check in order to see what Shape is doing for them. I have some customers that will leave this service running and never interact with it, but some of my customers are more interested in coming in and seeing this data point as well. So in here we have effectively what we're doing for the customer, whether it's serving JavaScript or serving other forms of response. If we're mitigating, of course, we're serving that response on behalf of our customer. So we can come in and see the data points here. So we might want to check some of the post requests, for example, that I've created as part of that attack. So these are all in green. So as I mentioned, I've used the bypass just to show those logins either working or not. But what we'll notice, of course, around this is that we've had a very regimented series of requests coming in from that Browser Automation Studio because it acts in a certain way. I didn't do a very good job of doing things like proxying my request across lots of different IPs and countries. So we're seeing here, for example, that all of my requests are coming in from the Netherlands. All of my requests are coming in from an IP address that's, or a singular IP address. We unfortunately can't rely on our attackers being this unsophisticated. They'll, of course, create lots of different ways of bypassing that. Equally, what we're seeing here is that we're just using a single user agent string for this particular interaction. Browser Automation Studio has ways of iterating through user agent strings or fingerprints of different browsers. So I can use some of those inbuilt tools of Browser Automation Studio to make my requests look a little bit more unique and stand out a little bit less than we've seen right here. And then I'll have, excuse me, my individual requests as part of this interaction set that we created. So if we were truly in our mitigation phase, I can look through all these data points. I can filter upon any of these. I can see the way that Shape has identified an attack if that has been the case. We can also see some of the raw data. So not particularly pretty. Some of our customers will ingest this into their own seams in order to collect it. But you can see some of the data points that we might collect that help us gain that picture. So I talked about emoji rendering. I talked about the way that floating point maths operations are calculated. We can see here that the math is moving a bit slow. There are consoles open. So we're seeing some other signals from this particular interaction pattern that give us the idea. We don't show all of the signals here, unfortunately. The more proprietary signals are kept on our data processing backend. But we've seen here some of the patterns and signals that let us identify this form of attack. So lots of data here. Of course, as I've said, in a real world scenario, we see a lot more data, and unfortunately, we can't rely on our attackers, I should say, being quite as unsophisticated as I have been today. They'll use proxy networks. They'll even do things like use residential IP addresses in order to bypass those IP reputation and rate limit controls. So let's go back to talking about the next step of those three questions that Shape will force attackers to lie about. So we've talked about that first question, fundamentally understanding whether the request is coming from a human or not. What we're doing now at Shape over the last couple of years is we've realized that some of the signals and the data and the machine learning patterns that we've created make us look or give us the ability to understand almost the intent of the human operator. Now, this role and this process becomes a lot easier once we've mitigated much of that bot traffic, because your data pipelines now are no longer corrupted with all of that bot data. We have the ability to look at the true human interaction patterns and much more accurately ascertain the difference between a legitimate good human and a bad human. Same sort of problem space though. Fundamentally, many of the forms of fraud that we combat might be down to the fact that there's a legitimate human logging in with their own username and password and even multi-factor authentication code. But there's also fraudsters who are doing things like using phishing or reverse phishing proxies or socially engineering their targets in order to get access to that information that allows them to log in. So gathering username and password, gathering the two-factor authentication codes through phishing or reverse proxies or social engineering allows them to commit the same sorts of fraud. Fundamentally, it's very difficult, again, for your existing security stack to ascertain the difference between a legitimate human and a bad human. And what we end up with this is, or what we end up, I should say, is with this, a graph that looks different to that first graph. This is fraudulent interaction patterns that we've identified using Shape signals. In fact, these were targeting one of our customers who had launched an unemployment benefits portal as part of their COVID response. So these are legitimate human users who are signing up for unemployment benefits because they can't work for COVID. Unfortunately, attackers are after this data and looking to commit fraud even in these trying times. The reason this graph is different is fairly obvious. It's number one, the scale is much lower. We're talking about rather than 60 odd million transactions, 531. So much lower scale of requests. But what we've done here is, of course, identified the patterns of human fraud that have been created using a similar set of technologies, either JavaScript or a mobile SDK, to find those patterns. So when we look at these forms of fraud, we'd expect those users to come from, again, residential IP addresses or proxy networks or Tor networks. They'll create very legitimate looking interaction patterns because more often than not, these forms of fraud are driven by a human. So the fraudster who intercepts that username and password and multi-factor authentication code is probably going to type that in themselves. So we can't rely on as many of those spoofing signals, although we can rely on the fact that fraudsters are probably going to want to try and hide their identity. So some spoofing that we collect, but the sorts of patterns that we look at are the way that the mouse moves for a fraudulent human user versus a legitimate human user. So again, these are some example signals. But a fraudulent user is much more likely to drag their mouse on and off the browser window, probably because, as you see here, what they have is a list of stolen PII or usernames and passwords and multi-factor authentication codes that they need to get into those boxes and they want to do very efficiently. So they're going to move, or the fraudster, I should say, will move their mouse on and off the screen to copy and paste and insert into those form fields. So we'll see unusual interaction patterns like that, or alt-tabbing. We'll also see, if we have a very good way, an accurate way of identifying devices, which at Shape we do, the fact that fraudsters are much more likely to log on to multiple accounts from a single device, whereas legitimate users tend to only access one or two accounts. If I think about myself at home, I only really log into my bank account, my spouse log into her own account from a single device. Fraudsters are probably going to churn through 8 or more different accounts in order to commit fraud. So we can look at the relationship between that device and the accounts that it's logging into in order to spot these patterns. Equally, if you're running a service from Europe or wherever it might be, you would expect most of the users to come within that time zone. Whereas if you're seeing lots of users logging in from Brasilia, logging in from China or Asia or elsewhere, you can start to spot the fact that there's something suspicious happening here. The challenge is, of course, that as you've seen from some of the numbers where we're talking about maybe 28% of fraudsters doing a particular thing, not one of those signals is accurate enough in isolation to truly identify fraud. So you need to put lots of different signals together, the way that the fraudster interacts with the page, where they come from, their device, what spoofing they're doing, in order to understand fraud truly. And in order to combine those in a very accurate way, you can't do that in a generalized fashion. What affects one of Shape's banking customers as they look at fraud is very different to one of Shape's retail customers or telcos. And the way that fraudsters interact with their applications is different every time. So we need to combine these features in a unique way, and often, in every instance, using machine learning in order to understand the patterns of fraud that correspond directly to this particular web application. So much harder to demo this sort of interaction because, of course, fraudsters tend to use applications very similarly to the way that we do, but we're looking and tuning for those particular signals that help us identify human-driven fraud, to understand intent, in order to understand fraud on these particular web and mobile applications. So the final component is, as we talked about, are you who you say you are? So once we've removed the bots and once we've removed the human fraudsters, what we're left with is a user. Now, that user is probably very used to entering their username and password. They do this every time. Maybe they forget the password, maybe they have to reset it or speak to someone in your customer support team. We talked about how capture introduced friction, but using a password introduces friction as well. It's not perfect. I truly hope that in my lifetime we'll find some other way of authenticating within applications. But what we've realized once again at Shape is that we can use some of the same signals that we've used to mitigate bots and fraud in order to prepare ourselves to treat legitimate users in a much more friction-right way. So if we understand the history of this device, have we seen this device before? Have we seen it commit fraud? Have we seen it across the Shape network? Have we seen this device log into multiple accounts or a single account? Is this device truly integral? Does it have integrity? Is it spoofing elements of its parameters? If we can put these 3 points together, we can understand, in fact, that this device used by Chris has not been involved in fraud. It's not logging into any other accounts. It's not spoofing any of its components. And we can then bypass the authentication process for that particular user. Now, the way that we do this will depend on your particular industry space, because, of course, something like financial services has a much more predefined set of authentication processes and timeouts under PSD2. But for our retailers, our telcos, they're using these data points in order to make Chris stay logged in for 30 days. The good thing about this is what we end up is often in our trials and POCs with our customers, a graph that looks like this. This is an A/B test of one of Shape's customers who is using this component in order to treat those legitimate users in a more friendly way. And you can see how the red and green are clearly diverged. Now, the red represents the users who are logging in manually. They had a session length of about an hour. So if they left the machine, if they went away, if they closed their laptop for the night, they had to log in again, maybe what was in their cart was lost. Whereas this particular customer consumed a data point that lets them understand when a user is good, when they've authenticated well, and they can stay logged into this service for days, weeks, and often up to months in many of the Shape cases. What that means is that we found that users who don't have to log in as often are much more likely to transact with your services. They are much more likely to buy. They're much more likely to buy more things more frequently. They might even buy different things on the same day. So for this particular customer, where we were treating this user as a good user, letting them stay logged in for, I think in this case, 14 days, we found that the conversion rates for this particular retailer diverged quite clearly, as you can see from the graph. We saw a 6.1 lift in conversion rate for those legitimate users. So for many of our customers, that will equate to multiple millions of dollars, or euros, or pounds in extra revenue. We've seen this happen across our retailers. We've seen it happen across the airline customers that we support as well. So if you're interested, please do let me know, and we can talk about how this might apply in your particular context and how we can start to use this data point. So slightly ahead of time today, but thank you for tuning in. What we've spoken about today is how we see attackers become very effective and adept at bypassing those existing controls. So when you're looking at your own services, as I mentioned, it's very useful often to monitor things like your login patterns. Very useful actually to monitor your login success rates, because attackers will log in often much less successfully than legitimate users. So watch for those particular patterns in order to help identify bots, and then consider using a service in order to mitigate those more sophisticated forms of attack that we saw today, even through things like bypassing capture or using Browser Automation Studio. We saw how human fraud is driven by those patterns, those unique patterns, and how you can identify those, how fraudsters will tend to act in different ways, and we can help you identify those. And then finally, we looked at the ways that if we understand legitimate human users, we can treat them in a much kinder way and let them interact and transact with our services much more frequently. So thank you for your time.